Hello, and welcome to Microreactors, Nuclear Power in Small Modular Packages, presented by the American Nuclear Society. This evening's event is part of our educator training program, specifically developed for elementary through high school teachers. My name is Eric Loewen. I'm the Chief Engineer at GE Hitachi Nuclear Energy and the former American Nuclear Society President. I'm pleased to have the opportunity to moderate this webinar on microreactors featuring Dr. Piyush Sabharwall. But before I introduce him, I'd like to go over a few quick notes regarding today's event. Questions, please type them into the Q&A feature of the Zoom meeting, and we will address as many questions as possible. We are recording tonight's event, and that link of the recording will be emailed to all of the event registrants tomorrow. Certification of the attendees are available on request. We'll put that into the chat of how you obtain your certificate of attendance. For the educators in the audience, please let us know if you would like to have an ANS member come visit your classroom, either in person or virtually in real life. And we have the request. It's ask anything@ans.org. And then for our ANS members that are listening tonight, ANS has a new Nuclear Ambassadors program that offers you as members free training so you can get into those classrooms from K to 12th grade and talk about nuclear engineering and education. So again, contact the staff or myself and we'll get you connected into that training program. So, and finally, the last is I ask that all participants adhere to the American Nuclear Society Code of Ethics. We have that on our website about respectful behavior, and you can find it there. So with those notes out of the way, I'd like to introduce our special guest, Dr. Piyush Sabharwall, who is a distinguished staff nuclear research scientist at Idaho National Laboratory, and we've had the opportunity to work together through our American Nuclear Society and his role at the Idaho National Laboratory. He has, for more than 18 years of research and development experience in nuclear engineering and thermal engineering. He manages the Radiation Experiment Thermal Hydraulics Advanced Department under the Nuclear Science and Technology Directorate at the Idaho National Laboratory. And in 2002, he was recognized as the Asian American Engineer of the Year. He also serves as a technical area lead on the Department of Energy's Office of Nuclear Energy's Microreactor Research and Development Program. So welcome and thank you all for attending, and I'll moderate the questions at the end of the seminar. Piyush, I turn it over to you.
Thanks, Eric. Thanks for the kind words. Just a correction, it was 2022 when I got that award, not 2002. But
what did I say?
You said 2002. So.
Oh, I forgot one number. Yes, it was. I have it written down as 2022. You made me nervous. Yes, 2022. Thank you.
All righty. Please let me know when you can see the screen.
Yes, I can see the screen.
Perfect. Thanks again, Eric. And good evening, everyone, and welcome to the seminar today. I'm really glad and excited to be here and in front of you talking about microreactor nuclear power in small modular package. And, I've been told that in attendees, we'll have teachers all the way from middle school to high school. So I'll do my best to provide the overview as much as I can. And here's my contact information. So please feel free to reach out to me if you have any question. I'll be more than happy to cover it if I'm not able to do it in given time today. So with that, I'll start. So when we hear the word nuclear, what do we envision? So I'm going to use a video to kind of talk about it or show people. So. Well, before I get deeper into microreactors or talk about microreactors, we learn and leverage from our past experience. So I always try to talk briefly about nuclear history, starting from December 1938, when fission was found, and our first reactor in 1942 was Chicago Pile 1, human-made self-sustaining nuclear chain reaction, also called CP1, when it all started. And then, as you can see, around from then till now, a lot of progress has been made. We had 1959 for transient reactor test facility treat, and we restarted in 2018. And before that, in 1951, we showed the criticality we showed EBR1 powering the electricity to the grid for the first time. So again, I'm not going to cover all the incidents here, but just saying that, from the past 1938 till today, a lot of things that happen in this field, we learn and leverage our experiences and apply that to our current reactors. Now, again, talking about history, where we are coming from, where we're headed. So I'm going to go on to the next video, which again talks about how it has evolved and where we are today. So before I get into that specifics, the question always comes, right? When we do any work or research, what is the motivation behind it, right? So why nuclear? Why nuclear power plants? What do they provide, right? Firstly, they provide energy independence as one of the clean energy sources, along with renewable technologies, stability and reliability of the electric grid. As some of you might be familiar, like a few years back, we were hit by the polar vortex in Texas, and even in that scenario, nuclear power plants were still running and working. Nuclear power provides highest capacity factor known, which ranges between 92 point something, 93%, which is very high for any energy technology. So it's a robust, resilient form of energy that we can depend upon. And it is a solution to achieve our environment stewardship going forward. Now, video here will just talk about where we came from and where we headed toward advanced nuclear. So. So, we've seen a couple of videos, and of course, Eric in his introduction talked about INL. So INL is the DOE Nuclear Energy Lab. Currently, it has close to 6,000 employees. We have three main directorates: Nuclear Science and Technology, Energy, Environment, Science and Technology, and National Homeland Security. So we have a lot of researchers, technical staff working towards meeting more goals towards environmental stewardship. As you can see, this is a pretty big lab with 890 square miles of area available, which is well characterized to deploy and demonstrate advanced reactor technologies. Now, with that history, now I'm going to start getting into main bulk of the talk today on microreactors. What do we call as microreactors? What are microreactors? So there was a definition based on the Infrastructure and Job Acts of 2021, which came out, which this is microreactors to reactors being between 0.1 to 50 megawatt electric. They're factory fabricated, easy transportable to and from site, have flexible operational lifetime between 5 and 20 years, and very well suited for communities like remote communities, isolated microgrids, mining sites, and DoD applications. So when this program started, we carried out a survey to see what microreactor concepts there are in US and what is industry interest. So based on the survey, we found out 4 reactor technologies which were under microreactors. One was gas-cooled microreactors, molten salt-cooled microreactors, liquid metal-cooled microreactors, and heat pipe-cooled microreactors. Again, based on the same survey, we found out which technology, which vendors are basically pursuing more of those technologies and what are the gaps that we can fulfill. So based on that, we picked 2 technologies that we primarily focus our effort on, which is heat pipe cooled reactors and gas cooled reactors. Again, continuing on the definition of microreactors, if you look at conventional light water reactors, you're looking at output of 1,000 megawatt electric, or more those are conventional. But here we talk about 20 megawatt electric output or less. Again, depending on your microreactor size and enrichment and your objective, this might vary, as I mentioned. So the main attributes that we look forward to about factory fabrication, transportable, and being self-regulated. Operation lifetimes being 5 to 20 years. These reactors, we try to make them passively safe as much as possible. So what I mean by that, when I say passively safe, is that we're not depending on any external source, like a pump to flow, to have a flow. We look at passive devices such as heat pipe devices that can transfer the heat. Right? Nuclear reactor in general is like a thermal engine, reducing that amount of heat. Now, how do you take that heat and apply it to the power cycle or other applications? So how do you get rid of the heat from the core? Right? So we want to do it in a passive manner. Now, the key possible markets that these microreactors are looking at, the remote mining operations, as I mentioned, military installations, university campuses, and you can go down the list. But the other one which I want to emphasize here is also the disaster relief. Sometimes, we get hit by tornadoes or tsunamis, like what happened in Puerto Rico. And, we want to make sure that the people there have access to clean energy and water. So if with this microreactor, we can meet that need and basically provide what's required in terms of energy for a smaller community. So, in that sort of scenarios. Currently, again, this list might not be complete. This is what we are currently aware of. These are the list of companies that we work closely with or reached out and said they have a concept they're developing, and we're trying to help them out as much as possible to basically help them deploy this technology. So as I said, you can see the developers mentioned, and the fuel, the coolant, moderator, and all those things are listed. Each concept is different. There are some similarities and some things do overlap, but some things are different. So we work with them independently and see how can we assist. Based on the application, here I've put this table together, which talks about power requirement. This is pretty general. I try to break these things down so it kind of, so people can see what sort of range is required for a particular application, like 500 watt to 10 kilowatt for deep space power. And then you have 1 megawatt, 10 megawatt, which is for military bases. Typically, this is the power requirement. So this table kind of tells you all that information. And then in these microreactors, we also, we're looking at non-LWR. So when I say non-LWR, non-light water reactors. So water is not the main coolant here. We're looking at different coolants. Could be liquid metal, could be gas, and then could be molten salt, or even heat pipes, which I'll get into in a few minutes. Now, the biggest thing, the first thing is this slide, I bought it from my colleague, Holly Tulu from LANL, Los Alamos National Lab, because this really puts this microreactor on one slide. So when we say microreactors, what is microreactor? Like, what comprises of, what materials put together comprise a microreactor? So if you think about these 6 things, right, you have fuel, the high temperature moderator, which is very important, especially with microreactors, because you want to get to the criticality in a in a compact fashion, right? So to get there, the moderator plays an essential role. Heat transfer power conversion, we are looking at different technologies. So currently, conventionally, we normally depend on Rankine cycle, which is again a water-based system, whereas other cycles which can give it to much higher temperatures and efficiency are called Brayton cycles, in which basically it's a gas-cooled cycle. So we're working with helium and open air and even the supercritical CO2 power conversion cycles. Structure materials, reflector, and instrumentation sensors. As you can imagine, right, when you put this compact geometry together, you want to make sure that you are able to monitor things. So your instrumentation and sensor have to, work in that confined manner because you don't have that much room. So you got to make sure your sensors are robust and can provide the required readings as required. Now, this Microreactor R&D, what are we basically, if you look at what areas are we working on? So as I mentioned, the key attributes, but being factory fabricated. So, if you have these attributes, mainly the factory fabrication, it helps you bring down your overnight capital cost, which is a big plus for these small energy systems. Now, coming back to the technologies, if you think about these 6 enabling technologies, so we're working in fuel and moderator area, because as I told you, fuel, we want to keep it, basically the fuel that people are looking at for this is HALEU, which is around between 5 to 19.75% enriched. And then we keep working on moderator to make sure that we can achieve those criticality with a small critical mass. Then we have reactor controls that we're working on, as I mentioned about the passive safety systems, power conversion to achieve higher efficiencies, and then structured materials, neutron reflector, and transport and sighting. So we're doing all this work in all these different categories in parallel and trying to meet those gaps. So this program, how is this structured? So under this program, the Microreactor program is subdivided into 4 areas. And all these areas are working, as I mentioned, simultaneously. So system integration analysis area is led by Oak Ridge, a colleague of mine, Alex Sunning, he's leading that. In this area, you're basically looking at understanding regulatory aspects, market aspects, right? Because that is very essential. End of the day, you want to understand what the customer needs are, so you can deliver the product which has value, right? Secondly, is technology maturation. So here you're looking at technology such as heat pipe, for an example. Like what do we understand in this? What are the shortcomings? What can we work on to fill in those gaps? This area is led by Holly Trulu from Los Alamos National Lab. Now, next thing is demonstration support capabilities, right? You want to demonstrate it at a smaller scale, right? And before you go put nuclear fuel in it and go critical, you want to do it in a non-nuclear test bed. This demonstration support capability is, in fact, I'm leading it at INL. In this, I'll talk about the facilities, what sort of facilities we have to achieve those things. And here, basically doing a non-nuclear. So you understand the thermal hydraulics behavior. When I say thermal hydraulics, I mean how the fluid moves inside, how the heat transfer occurs from the hot source to my sink. And then the other part, which is, of course, very important, is the application part. So as you can see, there's a reason the arrow is pointed up, because they all work together to get to the final goal of Microreactor application, which is a nuclear test bed, which I'll go towards the end of the slide, end of the presentation. Now, this program is, again, I know we talked quite about INL, but there are other labs also working simultaneously with us in different aspects. So we have an INL team listed on the right. We have Los Alamos team and Oak Ridge National Lab team. These are the folks helping in my area for the demonstration part. We have 2 facilities which are running and operational. Third facility is Hector, which is in design phase right now. Hector is going to be for helium component out of pilot research facilities, looking at much higher pressure and temperatures. Sphere facility is single primary heat extraction emulator, which is basically for heat pipe testing. As I mentioned, one of the microreactor types is heat pipe pool reactors. So, and I have a couple of slides on that, so I'm not going to go deep here. And the next one is magnet. So as I talked about the sphere, which is the single primary heat extraction removal emulator, right? Now, heat pipe have been used from in fact, let's say 2-3 decades already. We understand its functioning, okay? But the challenge is there are still some gaps, right? Because we want to understand not just steady state behavior, but also transient. So when I say transient, like what I mean is like when things change, right? When things change with respect to time. So I want to understand from startup to shutdown, right? So the heat pipe basically has alkali metal, right? They have water heat pipes of low temperature, but what we conventionally use in nuclear reactors are alkali metal heat pipes. When I say alkali, it could be the lithium, sodium, potassium, cesium, or you can have eutectic, like sodium, potassium, eutectic. So typically, you've been using sodium heat pipe. Now you want to understand the complete behavior, starting from when it starts the heating up from the evaporator end to the condenser end. So you want to understand the whole, profile, how is the temperature distributed. Some of the codes out there still assumes your alkali metal to be in a molten state, which is not the case because you got to provide heat to melt those things, right? Again, it's alkali metal, so it needs certain temperature to be molten. So we started this is a 20 kilowatt setup. When we did an experiment, it worked. But as you do these experiments, you learn and leverage. So as you can see, anyway, so we did this with the diameter 15 centimeter. But in a couple of cases, we saw that we were having some challenges. We were getting into some shortenings of thermocouples. Now, why did I put this slide? And I could just put this slide and talk about it, is because I know we have whole spectrum. We have teachers from high schools, maybe some students. So I want to get this message across. So when you do experiments, it's one thing to model and design it, but when you run it, you do encompass some challenges and you learn from those, right? Those failures are not failures if you learn from them and implement them. And that's what we did. So we learned from those the experiments, which we basically were not working as planned. So we modified the setup. And then with that modification, we realized there's more room for INC and we had less shortening of thermocouples. So we increased the dia, added more insulation because we noticed that we are having more heat loss. So we optimized the insulation for the setup. Again, this is a 220 kilowatt setup with maximum temperature that we can attain is 90 degrees Celsius. So we tested the heat pipe, which was part of ACT. We started with 1 kilowatt, operating temperature 70 degrees Celsius. As you can see at those temperatures, things glow. So that's the picture that you're going to see on the right. And we are able to produce results. So what we do is what we call as a successful shakedown testing. You might hear that term when you talk to experimentalists. So shakedown is like when you see a setup running, but you also verify and validate that your system is working as supposed to, your readings are working as it's supposed to. So you compare with something that is already run. So we compare our results with what was provided by ACT company, and things matched perfectly well, which gave us confidence in the setup and the way we were measuring things. We do this also at possibly a different orientation. So we can orient this at different angles to see the effect. And also look at instrumentation. What do I mean by that? So conventionally, we use thermocouples or pressure transducer for measuring pressure, thermocouples for temperature, right? But there are some fiber optic sensors that are being looked at. So we have both sort of sensors in it. So if a sensor failed, which has a low TRL level, which is technology readiness level, so we don't have much data to really have confidence in that setup, right? So we use conventional technique and these techniques that we are developing. So if we have a failure in those developing techniques, then we know what led to the failure, what changes need to be made. So that way we can learn from it and our instrumentation can evolve going forward. So it helps us with those things too. After doing that test, now we are also looking at some X-ray tests, this in operando. So how would this heat pipe behave when you can look, when it's running? And so basically when it's in operation, right? There's a wick structure in it. I'm not going to complicate things. Think about, you want to understand the flow inside, right? If I thermal cycle things, there's one thing to run something steady, but if you thermal cycle things, things might not behave as you expect them to behave. So you want to understand what led to the failure. Sometimes you don't get that by instrumentation. So we want to see when that happened. So this X imaging provides us that means. So we're building this setup to basically get there. So we can see if something fails, what led to the failure, and improve. Now, when you do experiments, right, before we run into experiments, we, of course, design things, model things, verify things, and try to reduce as much uncertainty as much as possible. At INL, we developed this framework called MOOSE, in which we are trying to couple structural, think about feedback from fuel, thermal hydraulics, and so in the same framework, so they can talk to each other. Because I want as much as realistic expectation from modeling. So the modeling results should infer my experiments and vice versa. So basically, if I can capture all the physics, all the things that's happening, then I can get as much close to as experiment as possible. So we do that, and we try to couple these tools together to understand how things would behave in the real experiment. And we learn from those things, modify the correlations with empirical correlations, try to put uncertainty to those things. So if somebody ran those experiments, they know what the uncertainty is, and they have a better idea how a particular component or a system would behave in the real prototypic environment. Again, I'm just talking about tool here. The idea is we look at a lot of flows, a lot of tools, incompressible flows, compressible flows, different flow regimes. We work with DOE NEAMS program, and provide, they talk to us, we talk to them saying what the challenges are. They tell us, we tell them what the needs are, and they provide us some help with the modeling tools. And we get back to them, and once we have experimental data, so they can validate those tools. And validation provides them confidence about how those tools behave. These are some examples. This slide just shows how those tools talk with each other and interact to get as close as possible to an experiment. Again, this is being developed in Moose at INL. Now, going back again to the experiment, so we talked about 20 kilowatt setup for Sphere, mainly focused on heat pipe cool testing. Now, if you remember in the beginning, I said that we picked up two concepts, heat pipe cool reactors and gas cool reactors. So in Magnet, which is 250 kilowatts setup, at that setup, now you're coming very close to industrial scale, and 2.2 MPa, which is megapascal or 22 bar. Here you want to understand a little bit more than what the Sphere can offer. So if you want to have a failure, we want to make sure we capture that failure at a much lower scale, like a 20 kilowatt scale. Once things pass there, then we can test at much higher scale in a Magnet setup. Here, we can go up to much higher temperatures. So basically I say 750, but if you look closely to the figure, to the picture here, it has veins in it. These veins have chilled water flowing in it. So this 750 is not taking that into account. This is only based on if I only use these gases to cool down or take the heat away from my test article. This is set up for 2.2 MPa that we can do for heat exchanger testing for gas cooled reactors. And also, again, instrumentation testing that may be passed in the Sphere. Now we can test at much challenging environment. And there, as you see, the test article size of the chamber size is 5 by 5 by 10, which is pretty substantial. Now, where am I going with all this, right? So the way this facility is located, it's in a building called ESL, which is Energy Systems Lab at INL. It's located next to TEDS and HTSC. Now, Magnet, think about this. Magnet is a source. My TEDS is my thermal energy distribution system, which is nothing more than energy storage, right? And HTSC, which is on the right, is my high temperature steam electrolysis. So I have a source in Magnet, then I have a storage in TEDS. TEDS basically uses alumina beads. It uses Therminol 66, which is a simulant for molten salt, mainly fluoride cooled reactors. And then we have a load, high temperature steam electrolysis. This is the means to produce hydrogen using steam electrolysis. Now, why is this important? Because this is how the real world is going to be, right? You produce certain amount of heat, certain amount of energy, but you don't normally all the time use it, right? There might be some times that you don't require that. Now, you don't want to have that energy that you produce to go as waste. What can you do to store that energy? That's where this TEDS come in. This coupling with my source, such as Magnet, with TEDS can provide that. That also gives me the data to look at charge and discharge cycles for storage. And then we can couple that with my load, which is producing hydrogen. Now, if I combine all this thing, this is the real industrial sector, right? Now think about power being produced, being supplied to grid. Grid is power, powering industries and houses. You charge a vehicle, the load is fluctuating. It's not a constant load. Ideally, you won't have constant load, like constant load and constant supply. That's an ideal scenario. But realistically, you don't get that. So how do you, make sure that things go as planned and you do something with that excess energy? So that's where the storage comes in. This is a pretty busy slide. It's not a confusion, just how that ESL array looks like. So we have that hydrogen I talked about, steam electrolysis. We have wireless charging place. We have additional real-time grid simulation. And we have this TEDS, which is on the bottom part, which basically uses Therminol 66, which is simulant for molten salt. Again, using just as energy storage medium. Now, as I talked about the reality, right? Where do we see how can nuclear play a bigger role? Now, nuclear coupled with other clean energy technologies such as wind, PV, solar, each technology has a different inertia, right? Different time scales. So how do we make sure that perturbation and all those things don't affect the grid? Our grid doesn't see that thing. Our customer don't see that thing. Can we do something about it? So this storage provides us a means to take care of those perturbations. All these are thermal engines, like I may keep mentioning. So these are technologies producing heat. You send that thermal energy to turbo machinery, turbine and generator, and produce electricity, right? But before that, it's just a source of thermal energy, right? If you, for example, if you need only so much electricity, you can provide that. But if there's access, you can provide that for other means. Like in my example, I talked about steam electrolysis to produce hydrogen, but you can use it for desal, which is desalination, produce clean water, district heating. So depending on the temperature requirement, you have low temperature process, intermediate temperature process, high temperature process, that you can basically meet a lot of energy needs, a lot of industrial needs. That's on the video, which basically shows the integration between nuclear and other renewable and other clean energy technologies. So in fact, I know that video talked about net zero, but can we even achieve carbon negative, right? And there are ways to do that, right? Integrated energy system really provides us the avenue to connect couple technologies, clean energy technologies like nuclear and renewable with storage, to basically take care of the perturbation and use energy when it's needed, right? Now, there are many, these are just few of the industries I'm mentioning here. But again, I'm going to emphasize, think about all these sources as thermal energy source, right? So you're producing heat. If you convert that heat, to have a means to basically use water as a cooling medium, so you produce steam. That steam can be fed into machinery in a Rankine cycle and produce electricity, right? But there are other industries that you can use, which basically use heat, right? Process heat for production of their products or even byproducts. For example, high temperature steam electrolysis, like you talked about, uses almost 80% heat and 20% electricity to get you vapor of hydrogen. There are many other industries that I mentioned here, which requires high temperature heat and electricity, which we can fulfill. And depending on the need, right, as I mentioned previously, if it's remote community, a small industry, a microreactor can meet that need in a very economic and eco-friendly fashion. So again, so I'm talking about the technology, I'm talking about the coupling, but then I have to also talk about the customer base, right? A few years back, we did a study with NREL, which is National Renewable Energy Lab. We looked at top 14 industries within US based on emissions, right? So we looked at EPA reports and stuff, and there were 14 industries as mentioned on the plot here, and this is how they're located. So the reason is, okay, we just want to understand what the requirements of these industries are. Is there anything that we can do using a microreactor or a small modular reactor, depending on the needs, right? So we went through all these 40 industries in details. When I say details, we looked at their process diagram, their heat requirement, the CO2 emissions, and then base it on what sort of reactor would meet that need, right? So I'm using an example here for our paper and paperboard industry. So normally, paper and paper industry, basically, most of them have their own power plant at where these industries are located. And most of the time, the main use of the reactor, more than electricity, is in drying process. As you can see in this, basically, when it goes through this biomass boiler into the turbines, we have these high pressure, medium pressure, low pressure steam. So instead of this boiler, we can replace, depending on the size of the power capacity required at a particular plant, either SMR could be a good fit or a microreactor, right? So the bottom line is this, right? If we do not put a carbon source on fire, we won't get CO2 on the back end. What do I mean by that? If you don't have, if you don't have C, right? Because if you combust C carbon with oxygen, you get CO2. But if you change that carbon, if you don't have carbon, if you have some other source, you will not get carbon dioxide on the back end. That's the important message there. So if we replace these energy sources, such as these boilers, with the nuclear microreactor plants, we can avoid those carbon emissions. The marine process requirements, like these are industries at various temperature requirements, right? So these are the industries I talked about. The 14 of those has different requirements. Current conventional reactors outlet temperatures around 300 degrees Celsius. But with these microreactors, advanced energy systems that I talk about, SMRs, we can push that limit, right? With molten salt reactors, you're looking around 650 to 700 degrees Celsius. With gas cooled, you can go from 750 to 900 degrees Celsius. So depending on the temperature need, you can meet these process heat requirements for these industries. So we talked about non-nuclear testing, right? And we talked about, okay, how can we integrate renewable to meet, eco-friendly goals? And then we talked about energy storage. We talked about research going in that area. So once we learn from these non-nuclear test beds, we apply that to a nuclear test bed, as Marvel, which is on the application side. This is an 85 kilowatt thermal reactor. Again, this being designed at INL and will be going critical in the next couple of years at INL. This is DOE authorized. So there's a big difference between DOE authorization and NRC regulated. So this is a DOE authorized, Department of Energy authorized reactor. It's 20 kilowatt electric. In this basis, again, I mentioned about 85 kilowatt electric, 85 kilowatt thermal, liquid metal thermal reactor. In this, you have sodium potassium eutectic as your main coolant, transferring energy to your eutectic gallium, tin, indium, and then it goes to Stirling engines. Those 4 cylinders that you see on top are the Stirling engines. And now the question comes, why are we looking at this, right? So when we started developing this, we wanted to make sure, first of all, we've not designed and developed a reactor or deployed it for a couple of decades, right? At a DOE site. So this would be a first of a kind in that regard. Secondly, we wanted to make sure to really achieve criticality at an accelerated time frame. We want to make sure to use components and parts that have high technology readiness level. For example, these Stirling engines, they have high TRL level. They are commercialized. You can buy that from a company, and that's what we did in that regard. But here we're looking at coupling of, as I said, sodium potassium eutectic with gallium, indium, and tin, which further pass on the energy to helium and so forth. So the idea here is a nuclear test bed, so we can do integrated energy system experiment with nuclear reactor, understand mechanics, and help other industries to see how the qualification process works. How do we go from just a paper reactor to a working reactor? It's around, as I mentioned, 7.5 metric tons and less than 15 feet tall. But even to get there, right, as I mentioned, you just cannot go critical. You want to understand key phenomena happening in your reactor system. So we designed and built at MFC, at INL, this setup called PCAP, which is Primary Coolant Apparatus Test. So what that is it has same size, same volume, except nuclear fuel. We basically use electrically heated rods to heat it, to understand how would it behave, how would the flow behave, are we able to get rid of the heat, how the system behave, when you couple this thing together. So there's a facility, Creative Engineers in Pennsylvania, which specializes in alkali metals. So so basically we did fabricate, develop this PCAT at INL, and then shipped it all the way from Idaho to Pennsylvania. That's where it is currently being tested. So again, this is a thermophysical twin of Marvel. If you want to understand things in this setup, in this prototypical setup, and learn from it, so we can basically improve things if needed, and basically help us validate the models, the modeling that we've done. We still need to validate those models to have confidence. So basically, recently we just completed a final design review. So the 90% design completion, which is a very big step where in a reactor deployment. And, so it's officially in the construction phase as we speak. Okay, apart from just Marvel, right? INL is also helping accelerate reactor demonstration. So what I mean by that, this slide, I know is pretty busy, but this is the amount of reactor vendors that we are working with. And this is the timeline of the deployment, right? So we'll be carrying out testing at INL in our nuclear test beds to test their performance and provide, back feedback, generate data to validate the model, because sometimes some correlations that we use, as you all know, right? When we design, there are some things that we assume, there are some things that have high uncertainty, and modeling can take us that far. But to take the next level, to really understand the complete scenario, how would it behave, we gotta go through some experimental testing. And that's what we'll be doing here, generating the data to support those models, support the deployment, and finding if their needs still there, or finding how can we optimize things, right? So this is the, as you can see, from 2024 to 2030, this whole spectrum of reactors, different coolants that we will be seeing at INL being going through demonstration deployment phase. So really exciting times at INL. We're working with a lot of industry folks on this. The two other test beds that we're utilizing at INL to help with us deployment is Enric Dome test bed, which is demonstration of operational microreactor experiments. It's less than 20 megawatt thermal, and it's establishing capabilities of existing infrastructure. Enric Lotus test bed has capability of 500 kilowatt heat rejection system, so that limits how big a reactor could be. And the dome that you see on the left-hand side, that's the EBR2 dome that we're using in this dome test bed. So, so I know I'm trying to cover quite a few things, trying to, couple those things, trying to see what the customers are, what the steps are to get there, and what's coming ahead at INL for testing, as far as testing is concerned. But for more information on the Microreactor program, there's a website that I would strongly encourage you to please take a look, which has program plan, like what's the plan for today, what's the plan for next 5 years, fact sheets on these test beds, operating conditions, what are the challenges, what we're working on, what we plan to test in future. Then we work with our industrial colleagues through a program called GAIN, Gateway for Accelerated Innovation in Nuclear. So this provides a means for industry partners to work with us at a national lab. And then we are developing these test bed on the DOE NRIC program. And then, as I mentioned in the beginning, we work very closely with our DOE counterparts. We had this work, all I talked about is in the DOE Microreactor program, but we work very closely with our modeling folks and DOE NEAMS program. So we work hand in hand, talk to each other, so we can help each other, provide the data so they can validate the tools, and they can tell us, okay, this is maybe has high uncertainty. Can you focus your instrumentation there so we have more data at a particular instance or a particular scenario? So this has been going great, and both programs are working together in a pretty effective manner. So in conclusion, we have exciting challenges ahead. As you saw, there's a lot going on at INL and in nuclear industry overall. We're still working on innovative ideas to further help us bring down the cost, and the demonstration is the key to really gain utility, regulator, and public confidence to deploy these advanced reactor systems such as microreactors and make them a reality for future. So with that, thank you all for listening. And as I mentioned, here's my email. So please feel free to reach out anytime, and I'll do my best to answer your question. Thank you.
All right, Piyush, got a lot of questions, so we're not going to let you off the hook just yet. One of the questions came from somebody who has worked in Antarctica for over 5 seasons, and their question was they were surprised not to see the molten salt reactors in the nuclear timeline. Why not?
So, okay, good question. So basically, I think so. Molten salt. If you look at molten salt reactor experience, we are limited with what we have from MSRE. Okay, it ran for a few years. We are still trying to figure out, a lot of things before we can say it's ready, right? So design is being made. We are understanding salt chemistry. We're understanding redox potential to avoid corrosion issues. Things we know, right? Things, as I mentioned, it's all about, I wish I could say all components are at higher TRL level, but that's not the case. We have to do these steps in modeling and testing at lower scale, medium scale, high scale to generate enough information to come to a point to deploy microreactors or molten salt reactors, in those sort of scenarios, So,
Okay.
yeah.
So with that, I think the next question kind of helps you. The question was from a different participant. Tell us about the technology readiness levels of the different microreactors that you shared tonight.
I wish I could answer that. As I mentioned, each vendor has their own design, right? Some of things overlap. For example, turbo machinery might overlap because they're using same sort of power cycle. But how they circulate the coolant, what type of fuel they use, what sort of control mechanism they have, what moderator they use. There are a lot of these questions which makes those reactors different with each other. So to really say one TRL number for any microreactor is very tough.
Agreed. It's a tough, having done it myself. So can you use a term called self-regulation?
Right.
Tell us, since you're a father, self-regulation means different things to different people. Tell us what self-regulation means in the context of what you shared tonight.
Perfect. So think like I started my talk and I spent some time on passive safety thing. So what we're trying to do here is self-regulate, right? So as the word itself says, can I design my system to be, in such a manner that it is safe no matter what? So I can add more defense in depth. It can regulate itself. So it sees those changes happening, right? But I have enough defense in depth in my heat sink so I can get rid of the heat from the core. It regulates itself. So it's not going beyond a point or so. The thing which comes to my mind is like, if a perturbation grows, if the amplitude grows, it becomes unstable. I don't want to get to that scenario, right? Simply put, because I know we might have some students from middle school. Think about this, right? If I have a ball on a hill, if I roll it down, it falls. It's no way it can come back up. But if it's a U-shaped thing, if I roll a ball, it eventually will stop, right? So my point is, when the ball going over the cliff is unstable scenario that I can't control. It has grown beyond a point. In the other scenario, it's controlled. So the ball is spinning, but then eventually it stops.
Okay, good. Now, you use the H word in your presentation, so you got to defend it, and that's the term HALEU. So if you could tell us what that acronym stands for, and then also do LEU and HEU so that we all understand those terms, please.
Sure. So HALEU is high assay, low enriched uranium. So basically, it's like if you look at the enrichment from 5% to 19.75%. So think like this, right? We want to achieve from a microreactor what we've been getting from conventional reactor, right? We have more fuel there. We have more things to play around with. Here, it's confined space. I want to get to criticality, but I'm confined with how much fuel enrichment I can use. Now, in that scenario, I have to look at these moderators and all those things to get to the criticality. So basically you have to play around with the structure. That's what I showed the slide. Those 6 things you have to play around with to get to criticality in a safe and a sustainable manner. Now, HEU is highly enriched, right? So it's 90% and above. But think about, for other applications, maybe we're not using that for commercial applications, but the objective there might be slightly different. Okay. And then we talk about low enriched uranium, basically keeping under 5%. And so those are the fuel enrichment ratios that we use and look at what we have to get to criticality. So.
Okay. So back when I worked at Idaho National Laboratory, we were talking about pebble bed reactors. So I haven't forgotten about them. Neither did one of our other participants tonight. What happened to pebble bed reactors, and could you use those in microreactors?
Yeah. So again, there are companies out there. Again, I'm here to talk about microreactors in general. So I'm not talking about companies, I'm not giving out names or for purpose, because I don't want to say I mentioned these 3 companies, but not these. So pebble bed also basically use triso particles, right? And they are being used as microreactor concept. They are used, and in fact, they have been found to be the most robust form of fuel out there. And we did a lot of work, basically giving history, because some folks might not know this. Triso particles it was a German concept, came from there. We developed our own. A lot of companies have worked on triso particles with different packing fraction. But again, we qualified the fuel at INL. So, that's what we did there. But yes, answering your question back here, gas cooled technology have 2 different concepts: prismatic and pebble bed. And they
Okay.
both are that. Mainly, again, coming back to you, yes, pebble bed are being looked at by companies for a microreactor. That is true.
All right. How about this question? Should I buy 10 microreactors or one reactor that is the same equivalent in power? So that's a question a respondent asked. What should we do for the grid?
Perfect. I'm glad somebody asked that question, right? And I wish I can say the answer in one line, but I have to kind of explain that. So depending on the need and the requirement, if my need is small, right? If it's a remote-based need, powering a hospital, powering a small community, so depending on the need, you got to look at, end of the day, right? You also look at what you get, how much, in nuclear also is looking at economics. You got to look at your payback period and operating cost and overnight capital cost. I'm not going to go in details in that aspect because that'll take me another half an hour. But answering this question is, depending on what your need is, it might make sense that you start with 1 or 2 microreactors and then add more as you need. But if you come in a spectrum of, say, 300 plus megawatt electric requirement, then you are talking about SMR, that you would like to go with. And if you have more need, like if it's a grid need, then more than likely you want to go with a conventional 1000 megawatt, because it doesn't make sense to have 110 megawatt electric than just one conventional. So, you got to look at what makes sense for what application you're after. Also, the other thing to think about is if you're not close to a water base, because these microreactors are liquid metal, gas cooled, or heat pipe, so you're not depending on a water source. So that also might be a figure of merit that one should look into. So,
okay, good. So now tell us, so you introduced the concept for heat pipes. Maybe for some it was new. Can you tell us how those behave inside this reactor that's producing neutrons? Do they get worn out? They have a limited lifetime. Could you share something with us on that?
right. So again, I will start with the background. So guys, and right now in our laptops and stuff, we already use heat pipes, right? So that's a good means of transferring heat. NASA uses it for our space missions. Now talking about radiation effect. So there were few heat pipes which were irradiated in EBR2 long time back, but that data is very limited. Okay. Heat pipe, people are looking at, still working on how do you get them to be more effective than they are currently today. So heat pipe is a passive device, right? It's transferring heat from an evaporator to adiabatic section to condenser section. So think about this, right? So my flow is happening on its own. Once I start the flow, it transfers the heat and almost at a constant isothermal temperature. So that's a big benefit. Now, why am I saying all those things? Because eventually, if I thermal cycle these things, they will not perform at the level they started with. It depends on the operation, so the cycle would vary. First. Second, in a radiation environment, yes, it's yet to seen how long we can say that these would work and what are the challenges. So that is something that we will look into down the road, right?
Okay.
Right now we're figuring out wick structures, best way. Wick is the means that, the coolant from condenser makes it back to the evaporator. So.
Okay. So you shared with us heat source, heat use. So you have this thermal transport. How does that system behave as a function of time? Does it get worse? Does it degrade? Can you share a little bit about the heat transport, if you will?
Yeah. So again, it might degrade because we are looking, as I mentioned, right? We want to try to balance the load, right? What we provide, demand and supply, right? So if you thermal cycle these things, now my structure where the heat pipes are in are going through constant expansion and contraction as the temperature is changing. Now, does that impact anything? What if my one heat pipe fails and I have this cascading failure? How far that failure goes, that again depends on quite a few factors. But coming back to this radiation and how this heat pipe heat transport mechanism would fail, if I'm not able to transfer the heat from my structure, the monolithic core, for instance, from evaporator to condenser, then that just becomes like a copper tube. It doesn't behave, it doesn't transfer the heat to the adjacent heat pipe. Now, if that happens, the load on my adjacent heat pipe goes up, and chance of having a failure for that heat pipe also goes up. So those are yet to be shown. Like, what I mean by that is like for hours of testing and in radiation environment, and that's the plan going forward. We will be carrying out the testing in future.
Okay, there's a question about Moose. Can you just give us a little bit more of that Idaho National Laboratory develops software, what it means?
Sure. So I'll try to put it very simply. So think about this, right? When we use a commercial tool, right, it does certain things. For example, if I get a fluid tool, fluid mechanics, CFD tool, it's just giving me those equations, governing equation, and solving those, and giving me velocity and temperature profiles. But it is more than that. In physical concept, I got to understand how the structure is behaving, how my material properties are changing with time. So it's just not one thermal hydraulic thing. I got to understand the fuel behavior. I got to understand the structural behavior. I got to understand my thermal hydraulics. Now, Moose is a platform that we're using with different tools to understand how they can relate to each other together. So it's not just solving one domain, it's solving those 3-4 domains and in a feedback form. So each of them are talking to each other. So you're not solving a problem in isolation. You're trying to solve the problem with all these things working together. So you get more realistic answer, which is much closer to an experiment, which sometimes the other tools are not able to provide.
Right, and I think, so we have a lot, this webinar has given us the most questions ever. So we're not going to get all the way through them. We'll talk about how we could answer them offline. So I'll just end with this one. Kind of a theme was, tell us about the security. Okay, you convinced us the technology works. It has passive safety. It's self-regulating, but what are the security concerns of all these distributed nuclear power plants?
Right. So again, that's a great question. So we are working with our folks in NNSA and different programs to understand that question about security.
Okay.
So let's come back, so if you take a step back, we talked about pebble bed, like TRISO. So those are the most robust way of securing to make sure that it's highly proliferation resistant, right? So you want to make sure we do that, we attain those things. And the fuel format is in a way that is very secure, right? Now, within the nation, yes, you can do it when we do transport these reactors outside. If a reactor makes it outside, if say, for example, there's a market outside and we do that, then basically we have to make sure that we have means in place to know where the fuel is all the time. And, so we need to have control of that. But again, even if, what my point is, what we have developed so far in the fuel is so robust and such high proliferation resistant that they can, the bad actors can't really do much, if I could say that.
Okay, so let's be good actors. We're going to end on time. I very much appreciated working with you again. It's been a while since you and I have worked together. Great presentation, great videos, really help communicate those, and hopefully our teachers that listen could use it and our ANS members can get in the classroom. So with that, we'll end tonight's webinar, and thank you all for attending.
Thank you. I'm glad to be here, and thank you. Please reach out to me if you have any questions.
Okay.
Take care. Bye-bye.